We present an exploration of the effect of headset luminance on user preference in VR. The world we live in is a very bright place. A typical indoor scene might have an average luminance under 100 nits, while specular reflections and sources can easily exceed 10,000 nits. Outdoor environments are far brighter, of course. We begin by transforming the Southampton, York natural scenes dataset, which contains 360-degree high dynamic range images captured in both indoor and outdoor environments, into an absolute luminance scale using a camera calibration we performed with the same hardware and exposure information given in the dataset. Then we built a headset on which we can display this dataset to study participants. We use a 60-watt chip-on-board LED as the backlight for each eye. A pair of Fresnel lenses directs the emission cone toward the eye box. This light is modulated by a transmissive color LCD followed by a transmissive monochrome LCD. Then the viewer looks through a Thorlabs 50mm achromatic doublet serving as the eyepiece. As you might imagine, the LEDs produce a lot of heat, which we dump into a mesh heatsink. A pair of fans draws cool air in from the bottom of the headset, over the heatsinks as well as the LCDs, and out the top. We also attached a Z-Mini tracker to the front to enable 6 degrees of freedom tracking. The resulting assembly can produce a tracked, stereoscopic VR image with over 20,000 nit peak luminance over a 62-degree field of view. Images shown on the display are decomposed into color and mono channels using a simple factorization. The monochrome display shows the square root of the desaturated target image using the sRGB color primaries. The color display shows the result of the monochromatic image being divided from the target image with a provision for 0 values. This simple approach can run on the GPU in real time for arbitrary content, with the drawback that crosstalk caused by the roughly 1mm propagation distance between the two displays is not accounted for, reducing the overall system MTF. We conduct a user study with 20 participants. A series of 19 stimuli from the luminance converted SINS dataset are presented on the headset. For each entry, the user is prompted to adjust the luminance of the headset in log offset steps to maintain constant scene contrast until the scene feels real and immersive. See our paper for further details about the study protocol. Here are the results from this subjective experiment. The yellow profile shows the ground truth mean luminance for each of the 19 scenes. In purple, we have the user responses when starting from the brightest state, and in blue, the responses starting from the darkest state. The profiles are the mean preferred luminance value with standard error bars. We see that the trend in indoor responses closely follows the true luminance values, especially for the start low responses. Preferred outdoor values trend higher but are likely capped by the peak luminance of the display. See our paper for further statistical analysis of these results. We conclude that users have an intrinsic preference for more brightness for outdoor scenes, and a moderate to strong correlation between physical luminance and preferred luminance for both types of scenes. Future work must look at the closely related effects of display contrast, and we hope to explore computational display approaches that may meet these preferences within the power and weight requirements of more practical headset designs.